So first of all, thank you very much for showing up after lunch. And when I mentioned to my colleague Mark Lundstrom that I'm going to Iowa, he said that he did not know that I was running for the president of the country. So I had to explain that no, I'm going to give a talk on Nanonet electronics. So it's going to be a very simple talk, and I hope that you'll be able to follow most of it without any complication. And my bottom tagline is that a complex need not be complicated. That is what I would like to explain in today's talk. So as you know, that electronics over the years have evolved quite a bit. And we have primarily focused on the top left corner, where we want to make transistors as small as possible, 1 billion of them if we can cram together. In a given year, TSMC makes more transistors than there are leaves on the trees. 10 to the power 17 is the number of transistors made. And so this has been a fantastic success. But sometimes this success obscures a set of equally impressive development in terms of solar cells, displays, and flexible electronics, where the important thing is to have large area. The performance need not be as high as a microprocessor. Of course, you are not going to run a solar cell at a gigahertz. It's a DC device, and you want to have power conversion for a long period of time, stable power conversion. And the requirement for such a system is that these are produced at low cost, at low processing temperature. Single crystalline, highly pure semiconductor is not necessarily a necessity, and in fact, it is counterproductive. So therefore, anytime you look at this new set of applications, whether they are in biosensing, whether in solar cells, flexible electronics, you continue to see an emergence of a new class of materials, which are presumably low cost, which can have flexible properties, lightweight, and often could be transparent, and so on and so forth. And the first thing that strikes you in these pictures are that these materials look awfully complicated. In fact, this particular picture looks like Jackson Pollock has run around and painted these nanotubes on a canvas. These are, of course, battery and organic solar cells, something Professor Dalal has worked on, Professor Chaudhary has worked on. So what I want to tell you is a story about these materials. When things look this complex, can you understand these devices in a way that gives you a fundamentally different way about thinking about these devices? Many counterintuitive results will immediately fall out if you understand the device as it wants to be understood. And let's see whether I can get there. So the trouble with this field is that field started, let's say, with Ohm's law, let's say. And as many of you know, that Ohm, today we take it as Ohm's law, of course, for conduction in metal. He was hounded from one university to another as being a professor unfit to teach because he proposed Ohm's law. It's only in 1850s that Ohm's law became widely accepted. And then came semiconductors, and we were very fortunate in our field that giants like Shockley and Cromer, others introduced a set of concepts like band diagram, minority carrier transport, that allowed such a complex device like a FinFET or any other type of structures to be understood intuitively and at an undergraduate level. The challenge is that when these materials came along, there's natural tendency that to use this has been so successful that to use this to understand these devices. But of course, that was not the purpose. And therefore, often you get things which makes no sense, mobility depending on the channel length. You have predictions which essentially, if you try to make these things homogeneous and try to optimize its properties, you come to a set of conclusions which are counterproductive. And even after millions of dollars spent, eventually you realize that that conclusions were not correct. And in last 7-8 years in Bell Labs, in Purdue, what I have tried to do is to bring these people, the other people who did in 1970s, developed this system understanding physics of transport through complex structure, bring to bear on these applications. And you will see that these are so simple and so intuitive that you will immediately see why they are relevant. And hopefully someday we'll teach these things in the same way that we teach the physics of crystalline devices. So I have essentially three parts to the talk. I will essentially focus on this part, which would be about 40 minutes or so, and then very quickly run through these two applications. And my goal is to show that if you understand percolation theory, you can do device design in a way, transistor design in a way that you wouldn't have thought otherwise. If you understand the notion of fractals, then you will design biosensors in a way that would define the fundamental limits. And if you understand phase transition, then all of a sudden people who never talk to each other, like solar cell people never talk to MEMS, and MEMS people never talk to steep threshold transistors, fundamentally all three essentially will actually they are solving the same problem. It is just that their perspective and the fragmentation in the departments or groups doesn't allow them to see the commonality. So these are the three things I want to tell you. So let me start with something simple, like a nanotube transistor. And I'm going to go through them, explain through them simply. You will be able to follow. So how does a nanotube transistor, carbon nanonet transistor is done? This is, so you have a substrate, you grow a bunch of nanowires or nanotubes on a given substrate. Then you transfer it to some solution, and that solution, you etch it off, transfer, and then that solution, you can spin coat it on any substrate. It could be a plastic substrate. It could be any substrate that you desire. And the point is to decouple the process from the final substrate. This is not, of course, what we do for silicon. Silicon, the process, the substrate we carry from the process to the final device, it decouples the two, and therefore it allows you to put things on flexible electronics, although the individual quality of the nanowires, they are fantastic because they were grown at high temperature. So this is the mix of high performance and flexible substrate that is you wouldn't get anywhere else. So that is an interesting combination. And then what you do is essentially you can also do nanotransfer printing, essentially have a circuit, grow them, and then transfer them, just like transfer of a stamp. You can transfer them on a circuit. So at the end of the day, and I'm going through this quickly, just to say that at the end of the day, you can get any complicated circuit you want based on transistors that has a bunch of network of carbon nanotubes on it. Why do you need a network? Because then you can flex it. And therefore, it will not performance can be modulated, or will not be modulated simply by flexing. Now, how would you design a transistor like this? That is the question that I want to ask and answer. By the way, if you could do something like this, then you could make circuit like this. So this is a paper that came out a few years ago from our John Rogers and our collaboration. And I want to tell you how percolation made this transition possible. If you simply make these devices and try to make the circuit, none of the circuit will ever work. And I'll explain why. So there is an important component of theory that you will see comes into play. So I knew that when there is a network like this, you should be using percolation theory. So I didn't know anything about percolation. So I went to the library. That's what people should do. And I looked up percolation papers. Of course, there are lots of percolation problems. Telecom grid in Paris, network and World Wide Web transport through that, lots of stochastic geometry and aerosol filter, lots of qualitative discussion, but no engineering application of percolation. Percolation always is an interpretive tool. You see something and then you write in your discussion of a paper, it can be explained by percolation, but not the engineering of it. And that's what it was missing. In fact, if you look at the literature, the entire literature, that if you have a paper, let's say a conducting paper, you punch a hole in it, and when you have sufficient amount of holes, all of a sudden the conductivity will go away. And 20 years later, people had been looking at the same thing with a slightly different system. But of course, none of this you could use for the Nanonet, where you have a bunch of carbon nanotube, because these are not transistor structures to begin with. These are two-terminal structures. You have to do something more than what you can find in the library. Okay, so this is the problem, and so when you cannot find things in the library, it's better to push away the books and take a pencil and paper out. So this is the pencil and paper configuration. I'm thinking about a transistor which has a source and a drain. I have a gate in the back, and by applying a voltage on the gate, I can turn the transistors or the nanotubes on and off. And this is like a normal semiconductor channel. If you had a FinFET, you apply a gate, carrier concentration gets modulated, and therefore you can turn things on and off. But the problem you immediately see that things are not so easy. If you look from the top, then you can see that tubes are all over the place. Some are crossing directly, some with an angle, some with all sorts of starting position. How are you going to design a transistor around it? And then it came to me that actually this problem can be easily solved. First of all, my question about can I solve one? Yes, I can just take up undergraduate semiconductor device textbook, and essentially what I can do, just like the transport property for each one transistor. But you see, what you can do is that if you take a starting point and then collect everybody who starts together, then you'll immediately have a Japanese fan diagram type structure. And in fact, so what you'll have is you'll have a structure like this. So although this structure looks completely random, in fact, actually all you have to do, this image is not 100% right, it's 50 to the left, but depending on where it starts, the ending point, there is a certain angle relationship. If its angle is more, then therefore it cannot bridge the gap, and farther away it starts, the narrower is the angle through which it can bridge. So then you can sum it up. And if you can sum it up, then it will give you some interesting results. By the way, when I thought about this, I thought that this was a very clever idea. I was very excited. It turned out that this is actually a problem that was solved about 200 years ago, because just like Descartes has connected algebra with geometry, the person who connected statistics with geometry is this person. And this is called a generalized Buffon needle problem. You throw a random needle and see how it crosses a pair of lines. So you sum them up. That's not a rocket science. Anybody can do it. So you sum them up individually. For individual tube, you take the normal MOSFET characteristics. This L is the length of the intercepted region from here to here. And the voltage dependence of the drain and a gate is taken from an undergraduate textbook for a single transistor. And all you have to do is to sum them up. So I'm summing it up. And of course, as I said, that given an initial point, you know the angle. So you go through the math, and at the end, you get some result. Now, I'll not ask you to derive this result. It's not complicated. But the important thing is this, that at the end of the day, what you find that the current in a network structure like this, random network structure like this, will always decompose into two parts. One part that depends solely on electrical properties, the drain voltage, gate voltage, and so on and so forth. and another part that depends solely on geometry. So like here, this is the geometry, this is the bias. And it will always decouple, because anytime you do a space integration, this voltage will come out. And therefore, and this really depends on two scaling variables. It depends on how long your stick is compared to your channel. That makes sense. If your stick is smaller than the channel, it's never going to bridge. So that makes sense. The other one is the density that you have, number of nanowires you have, that's the density multiplied by the length. So these two are the scaling variable, and there is this partition. So let's keep this in mind, because this is not the problem I'm trying to solve. I'm trying to get a back of the envelope calculation to start solve something which is deeper. So
what's lambda here in the first equation?
Lambda is the mean free path. When the transistors are very, very small, let's say less than 50 nanometer, 30 nanometer, then the 1/L dependence doesn't work, because electrons are going ballistic. And so therefore, you can see it's very small L. It will go away, and so this will become proportional to the ballistic transport. So this one will automatically go from the diffusive limit to the ballistic limit. So this is a formula, by the way. This part is what can be obtained from classical percolation theory. All the work in 1970s, all the three big person I showed you, Mandelbrot, and then the percolation, other percolation work, this part was always known, but they didn't have transistor. So therefore, this was not known, and that it comes with a little multiplication product, that was also not known. So therefore, I essentially married two people, Shockley and the people who work with the percolation theory with the multiplication sign. We'll see whether it works and what engineering can you do with it, because that will be very interesting. So before I go further, so the original problem that we looked into, or want to solve actually, not the little problem, is a network problem, because here the electrons will climb up, then they will transfer to another, then they will transfer, and then they will go to the other side. Random network problem. That is what we are really after. And we will have a source, and we'll have a drain, and there'll be a back gate which will turn things on and off, and it could be front gate also. And of course, I work with a Purdue who is very good. All I have to do is to find a good student and be very nice and ask them to solve a particular problem. There are big computers, so people can solve it. You can solve the Poisson equation, which gets electrostatics, nonlinear potential drop. Those things all you can do anytime you are going from one highway to another. This is the transfer coefficient from one highway to another. If the resistance is, if there's an oxide layer, transfer will be very poor. If it's good contact, transfer will be very good. Cij will know about it. So this is tube-tube transfer. And you will solve all these problems. After a couple of days, the student will come back and give you some results. The thing that the person will give you will immediately make you worried, because the first thing they will say that Ohm's law is wrong. Now that seems very provocative statement to say, but in 2 minutes I want to explain to you that why this is obvious. First of all, if the density, so these are for various nanotube densities, if the density is very high, 10 per micron, let's say, micron square, then Ohm's law is valid. It's a log-log plot, and a straight line with a -1 slope tells you that Ohm's law is fine, that as you make the things longer and longer, your conductivity goes down as 1/L. That's Ohm's law. On the other hand, if your density is low, 1 per micron square, all of a sudden, Ohm's law is not only invalid, it goes as 1/L squared. So Ohm's law is invalid means your mobility is wrong, your compact models is wrong, everything is wrong. So why is it? Makes very simple sense. These are the calculation. You have a given channel length. The red ones are the conducting pathways, and the blue ones are sort of hanging branches. And so therefore, they are not carrying any current. And so therefore, as you make your channel length from here to here to here, then of course, you can see that the current will increase 1 over L. That's understood. That's Ohm's law. On the other hand, think about this case when the density is low. When the density is low, then this is what's going to happen. When you are far apart, the two contacts are far apart, there is no percolation path that allows you to go from here to here. Because density is low, there's no path, direct path. When you bring the paths together, pairs together, all of a sudden, you have one percolation path. As you bring it even closer, you have a bunch of percolation paths. Now, does it make sense to you? Think about in early days in the United States, you want to go from New York to the West Coast. Percolation is 0 because there are very few places where there's a full connected path from one side to another. But if you wanted to go from New York to here, there are more probabilities. And if you want to go from New York to New Jersey, there are many paths. This is what you're seeing, that when the density of paths are small, then therefore, you have this phenomena. What this it automatically says that not only the length is going down, but the effective quote-unquote width is going up with the length. Because you see here you have 4, here you have 1. So the width is a function of the length. That is why it goes as 1 over L squared. And that is a classical result of percolation theory. And in fact, it turns out that this exponent, which depends on the density, remember the scaling variable I told you about? Ls over Lc is one scaling variable, and this is the other scaling variable. And this scaling variable says that this would be 2, because this will go like this with a slope of 2. In fact, if you do infinite percolation system, there is a precise value, 1.89356. But for electrical engineers, it is 2. So you get the idea that percolation system is, by definition, is a very different object. Anytime you have polycrystalline material, random systems, you cannot just use a Ohm's law to do its engineering and device design.
In this case, the assumption of Ohm's law doesn't hold either.
Right. Now, Ohm's law has two, yeah.
There is a connectivity requirement.
Yes, but Ohm's didn't really do any of this. Ohm's had a set of data, and the reason he was so strongly condemned is because those days the batteries were not very well calibrated, and he was putting too high a voltage. And so if you look at the original, he published a little booklet. If you look at the original data, the self-heating essentially turned the curve. That he was fitting with a straight line, this is most people found it objectionable. It's clearly a curved line, and he is saying it's straight line. So that was something else, self-heating. We are not talking about self-heating. But you are right, that it is, in that sense, built in. Now, you can immediately see that if you now take a MOSFET, let's say, I'm not the professor, the students, your advisor tells you that here is a MOSFET, please go and fit it, get the IV characteristics done. So you go on the IV characteristics, and you plot it as a function of 1 over L, and then you calculate the mobility. That's how we do. The rest of the things contain the mobility. Now, of course, what will happen now, because Ohm's law is invalid, 1 over L doesn't hold. And so therefore, if you calculate a mobility, which is the derivative with respect to the drain current as a function of gate voltage, will now be length dependent. If M is 1, then you don't have any length dependence, Ohm's law, or normal long channel transistor theory that we learn in our classes. But in a percolation network, when M is 2, every mobility, if you have 3 micron channel, you have 1 mobility. You have a 2 micron channel, you have a different mobility. Your models are never going to work for such a system. Now, these things seem simple in this way, but of course, you don't see this network when you're looking at a picture, right? So therefore, it's very counterintuitive. And first time you point it out, it's not something easy to convince people that things are correct. All right, so I told you about the network geometry, that how percolation theory only with 2 scaling variables can describe the network geometry. What about voltage? This is something percolation people never solved. So you have a source grounded, drain, let's say put 100 millivolts. Another, same transistor, you put 0, ground, and put a volt. You know, we turn on the transistor drain voltage, we turn on and off. Now, of course, this is a problem in 1970s, 80s, people couldn't solve. They didn't have the computer, and they didn't really were applying it to transistors. But the student immediately solved it. And you know what I am expecting here, because I know the result. I expect, if things are reasonable, I expect this geometrical function to be multiplied by this. What it means that, look at, this is very nonlinear potential. This is a pinch-off region, very nonlinear one, because the length for this one is not the same for length of this one. So therefore, it is a very non-trivial pinch-off region. But I expect this relationship. Therefore, if I divide ID with this factor, because this factor is invariant, independent of voltage, then, or I'm sorry, ID with this voltage, where VD1 and then I have VD2, then they should give me the same result. That is, if I normalize all the voltages with respect to VD, they should be on top of each other if this scaling theory is correct. Right? You have two different voltages, and sure enough, they are, this is numerical simulation, of course. They are on top of each other. So this decoupling, at least in the modeling, which you should never believe 100%, is on top of each other. And so it says that this deconvolution in terms of geometry and voltage are absolutely fine. But does it really work in complex structures? It wouldn't, I wouldn't show you if it didn't. You say that indeed this is the case. So these are all the experimental data as a function of L. This is L is -1. This is from L is about 1.5. Clearly, this is a violation of the Ohm's law. And the thing is that whether you do it at 3 millivolt or you do it at 1 volt, this gets shifted because this comes from the geometry. And this is for 30 millivolt. This is for a volt, IV characteristics. Again, because of this factor, it just got shifted by amount. So therefore, this nonlinear generalization of the percolation theory is experimentally verified. By the way, all these data points are not from our group. It's from John Rogers. So we work together, but he's very good because he wants to check every assumption that goes into the system. And I'll show you what it leads to. So in fact, later on, I'm not sure whether you can see. No, the quality is not very good, so you cannot probably see. In fact, with the voltage contrast, you can see all the lighted up paths going through this network, and it looks beautiful. And so maybe with a lower light intensity, you could have seen this, but I will show you some more. Oh, I think these are for different voltages. Do you see this? Maybe I should have made a little movie. The low voltage, high voltage, and then gradually increase the voltage. And when you increase the voltage, then essentially you can take the images and scale on top of each other. They will all fit perfectly. Okay. Yes.
Would those nanomaterial migrate or shift under the voltage? This will make the calculation more complex.
Yes, yes.
Will they also move around?
Move around. If they move around, if the network is dynamic, that will be even more complicated. But these are assumed
There's no moving.
Not many moving, because these are carbon nanotube on a substrate. And so this is not any moving anywhere. Yeah. Now, one thing that I didn't tell you so far is that actually carbon nanotubes have come in two variants. One is called a metallic and another semiconducting, 2/3, 1/3 ratio. So for every 2 semiconducting, there's 1 metallic tubes, and that makes design with carbon nanotubes a nightmare. Because you can have very low density, so that the red metallic tubes don't percolate, only the semiconducting tubes percolate. The density is so low, so you can turn things on and off. But density is so low, your current is horrible. But you can turn it on and off. So then you get a little greedy. So you say, okay, I'm going to increase the density because I want more current. But as soon as you want more current, this red metallic tubes are going to short you. All on a sudden, you had 4 orders of magnitude, and you have hardly factor of 3. And then if you go, it will be exactly a factor of 3. Your transistor is dead because essentially it's shorted. You cannot turn it on and off. This was a problem that stayed about 10 years in the field. How do you solve a problem like this? Because here you have to play with density. Every time you change your channel length, you have needed different density. How are you going to design a circuit with it? It turns out that you can do something very simple. What happened here, you see, the problem is you want the metallic tubes to be below percolation and this semiconducting tube to be above percolation, and this is the percolation threshold. Now, of course, the trouble is that every time you want to do it, it's difficult to exactly precisely. Can you do something else? That now, so the second case is this, that when they are both above percolation, then you have problem. And the third case is that one when then you are dead. But the thing is that can you do something so that the system works even without doing anything to the density? And here you will see how failures of Ohm's law can become a powerful engineering tool. Assume that you cut the transistor into a bunch of parallel channels. Normal transistors, nothing will happen because you see, you cut, let's say, in 4 pieces, current is 1/4, you sum them up, current is the same as before. Normal Ohm's law would say cutting a channel in the middle does really do you no good. But that's not the case for carbon nanotube, because anytime you cut it, you can move the percolation threshold. Do you understand this? So let's say this was your original percolation. Now, the metallic tubes were just hanging by because they had fewer paths to go direct. That is all metallic. You need all metallic. And there were quite a few blue semiconducting paths. So that's okay. When you cut the poor metallic ones, they get disproportionately cut. And as a result, there is this continuous metallic path that could go from source to drain is no longer there. So the metallic paths are removed effectively just by cutting, and semiconducting paths are intact, because semiconducting are at the ohm limit and the metallic are in the non-ohmic limit. As a result, it will allow you, so there are all this theory work that I have published quite a bit, and will give you a transistor that is fully functional. So you start with a transistor, none of them works, you come in with a laser, do a few stripes, whole circuit begins to work. So this is what the original one was. This is the simulation. And after cutting, this is the width. So when you make it very big, then of course you have very poor on-off ratio, 3:1. You cut it at different length, and at some point, depending on the density, all of a sudden metallic tubes will not be able to percolate. Of course, there are metallic tubes in here, but they need semiconductings to go through. And the semiconductors will be modulated by the back gate. And your current on-off ratio will go up by 5 orders of magnitude, simply by cutting. And as a result, this is experiments. And these are the experimental verification. And this is how this circuit is made. You cannot make a circuit if you do not know percolation theory, because this was the transistor that involved about a couple of thousand transistors. And none of them would have worked if you didn't know how to handle it. Yes, please.
Don't the metallic ones burn once you pass the current?
No, this is a very low voltage, very low voltage, operation voltage. Yes.
Did you try with first aligning those carbon nanotube between S and D so that maybe you can reduce the complexity?
Reduce which one?
So here, those carbon nanotubes are crossed together over between S and D.
Right.
But I also saw some research ongoing say they can align the carbon nanotube between S and D so that you can reduce the complexity.
So what he asked is a very good question. That do I need it to be random?
Right.
Could I not simply align it?
Right.
What happens when you have a relatively long channel transistor, many of these are long, you need a certain amount of drive current, then what happens that alignment is actually worse because percolation threshold is infinity. because it's always possible that the two will not perfectly align. Here you always have a chance that you will be able to go from here to here. You will take a complicated path, but you will be able to go. But if the things are aligned, let's say next one is not perfectly aligned to this one, then the whole thing is broken. Now, of course, if your channel is very short, makes a lot of sense to align. But we are thinking about thin film transistors with long channels. Yes?
So, this cutting trick, it's a geometric change.
Yes.
So which parameter in that geometric part gets modulated?
Oh, so I think, I'm just giving you a very quick theory. So effectively, LS over K. So I did a complete theory of the percolation of this finite size percolation of this type of network, because normal percolation books are all infinite system, a length and width are the same. And essentially, it's like a effective stick length got cut by a factor. And the K is different for metallic and semiconducting tubes.
Can I have a follow-up question?
Sure.
For the mechanical common tube and the semiconducting common tube, actually right now, if you can purify.
Yes. But there is
Semiconducting.
yeah, the challenge is this, that you see, if you purify that way, there are companies, Harsham's company does that. But anytime you do solution processing, the eventual transistor you make is not very high performing because the mobility is never very high. So you can get all 99.99% perfect. And then in that case, if you want to do that, then that's also possible. What I'm trying to say is that just as an illustration, I want to show you a few more where you see just by thinking about percolation. Of course, we can solve the problem in the material level. Then that's always good. But you can solve problems in the engineering or geometry level. That's what I am trying to focus on. Yes, please.
How do this laser factor the cost or the manufacturing speed of
So what is done is essentially you have this carbon nanotubes, the whole substrate, and it just cuts in long lines. And then you put down your source drain and the entire circuit on top of it. So therefore, it is cut in one shot. You don't cut it after, because after then it may not be, you have metals and all sorts of things. So you cut the fabric, not the contacts. Okay, so if you thought that this is negative percolation doping, this cutting is good, I have to show you something where the opposite is good. So let's see whether. So what I'm trying to talk about here now is about a solar cell. And solar cell has a conductor on the top, which is transparent, because sunlight has to get in, and the electron hole pair that are generated has to get out. So it has to be transparent. People generally use ITO. It's a oxide. It's generally very good, works very well, low resistance, good, but it's generally unstable. And 1/3 of the cost in solar cells often is associated with this. So when people thought about graphene, the people have to write proposals on graphene. So they said, okay, we'll use graphene because graphene is very thin, highly conducting, and it will be transparent. And so therefore, it will be a perfect replacement of ITO. That makes sense. Only thing that most people don't realize, which is not in the area, is that graphene is a horrible conductor. Because when you put two contacts very close by, then it's a very good conductor. But if you want to put a conductor here and here, then there are so many polycrystalline grain boundaries that essentially this is one of the poorer conductors that you can find. Almost many other materials are better than this. And the reason is that you have this low angle and high angle grain boundary on the copper substrate. When you grow, then the multiple things merge, some at low angle so the current can go easy, and some at high angle so that current will just get trapped and will not be able to go. So this is your life. You cannot beat this. And the question is, again, percolation problem. Shouldn't we be able to do something about it? So this is an example. If the grain boundaries did not matter, that all had very little resistance, so then it doesn't matter. Then the whole thing, current could go from source to drain or from one contact to another through the grain boundaries. It's as if Ohm's law and a normal ohmic conductor. But that's not what happens. What happens is that you have this high resistance grain boundaries. And the current tries to go but it gets trapped. And so therefore, it has very, very poor conductivity. And you can easily see that if you increase the grain boundary percent, the resistance is going to, so nature and science you report here. But by the time you actually look at large conductors, it is about 67% or so. The conductivity has dropped by 1 or 2 orders of magnitude. So what are you going to do that will help you solve this problem?
The color picture up there, the contrast, is it because there are multiple
Grain orientation.
one single layer of graphene?
One single layer of graphene. It's not patchwork. It is just multiple grains. So then the idea is simple. Previously, by cutting, you could open things. You cannot cut grain boundaries. But what you can do is to sprinkle a few nanowires on the system, statistically, randomly throw them on. And if you throw them, now all of a sudden the grain boundaries which were there, now you have just provided a bridge. So if it doesn't like to go through that barrier, it will climb up. And now would it want to climb up? Yes, because it has a lot of space to climb up. If it were very small, then resistance would be very high. But this has this region to climb up and it will go. But of course, you cannot have just pure carbon nanotube because that also has a very high resistance. And in that case, the graphene provides a path underneath. So anytime it doesn't like the carbon nanotube barrier, graphene allows you to go. And anytime it doesn't like graphene, it uses carbon nanotube to go. It's a co-percolating system. Now this one, however, will do something amazing because previously this is how the resistance was dropping as a function of various grain boundary proportion. And all of a sudden, with a small amount of this nanowires thrown in, your resistance will go up by orders of magnitude. That's the theoretical prediction. And it's very simple. We see if you have two resistances which are comparable, R1 and R2, we know that it would be on the order of the smaller ones. The resistance would be on the order of smaller ones. Here you put R1 and R2, two networks, and the total resistance is a order magnitude below the lowest one. That is something that will never happen in a ohmic conductor. So these devices, we made these devices, and we made it in different ways, but the one that we had most success was that we had a carbon nanotube network or silver nanowire network, and then we wrapped graphene around it. I'll explain to you why this one is better. You could have the other way around. You could have graphene on the bottom and silver nanowire on the top. Let's see how it behaves. So this is, So this is how it looks like, pure silver nanowire network. And so you have this network, and this is wrapped. It's like a cellophane wrapped. So the graphene is wrapping on top of it. And you can immediately, if you take a thermal reflectance image, you can see that this network, this is a central electrode, and there is a circular TLM. Central electrode, and see it's like it is burning up because resistance is so high that at a given voltage, then there is or a given current level, that there is this thing is very highly resistive. That's why it shows up. As soon as you throw in a little graphene, it's like putting like water on fire because all these hot spots disappear. Now, how good is it? So the transparency is above 90%. And so there are a bunch of various results for various densities. But the first important point I want to show you that if you expose silver outside in the environment, come back 2 days later, it's all gone. Gone meaning that resistance will become horrible, right? That's why silver jewelry, my wife wouldn't really like it very much. But on the other hand, if you put it graphene on, then all of a sudden the graphene protects you from the environment, and this has been there for 2 years. And we periodically go back and measure its resistance. It is as good as when it was made, in fact, slightly better. And so this is the summary of this part. Before we started this research, this is a transparency. You need high transparency, and you need low sheet resistance. So you want to be here. That's good. And here is bad. On this side is bad. And this is plots everything that has been in the literature, Samsung and every other, whoever has reported it. And you can see that this graphene network not only provides higher transparency, it does so at a lower resistance compared to ITO or anything single graphene or single nanowire network has ever done. Again, is an example of percolation doping and non-ohmic conduction. So let me not go through too much detail. I think how many minutes do I have? So about 5. So I think maybe I should skip a little. I think I wanted to show you about organics. Maybe I don't show. Let me skip this because I don't think I can, in 5 minutes, I can go through all this. I will skip this part and then I will just go wrap up in the. So I told you about these two systems and didn't have time to discuss really this. I want to quickly tell you that what I learned about from all this. I've been doing this for a few years. What did I learn? The first problem I want to tell you is about the connection about different systems. Because when you view it in the right light, many problems that look completely uncorrelated or completely disjoint turns out to be the same problem. So here are 3 structures. One is 2 polymers, which are basis of organic solar cell. There is a donor and acceptor. And when you raise the temperature, it phase segregates. And this physics of phase segregation is described by Landau theory, because you have an energy landscape where once you raise the temperature, essentially it does mixing, demixing, and so it will be either donor rich or acceptor rich. Now, what many times one doesn't realize that if you have a MEMS structure, MEMS is exactly described by a structure like this. So MEMS, what is a MEMS? It is a parallel plate capacitor. You apply a voltage, small voltage, it comes down and it gets stabilized. Put a little bit more, comes down. But then you apply a tiny voltage, millivolt even, beyond a certain voltage called a critical voltage, and it will snap shut. There is no stable state in between. And you can also show just a few lines of algebra that this is described by the same energy landscape. That what happens that you have this 2 stable state. As you apply the voltage, you push this one up, push this one down, there's a stable state. And at some point when you push it up, the whole thing rolls on the other state. And therefore, it snaps shut. This one is a ferroelectric. Ferroelectric is a material which has a permanent moment. And it turns out this is really a trillions and trillions of MEMS in parallel, because there is a central atom which essentially like a slingshot goes to the one side or the other. That's where the polarization comes from. So all 3 have the same fundamental energy landscape. As a result, you can solve problems in one field and borrow the ideas and solve a whole set of problems in the other field. So for example, we wrote 3 papers. One paper was the degradation of organic solar cells. The other was dynamic soft landing. How do you soften the landing? Because it comes down so hard that it gets stuck, and you cannot unstuck it. This is a fundamental reliability problem. And then this hot atom, as the atom is for the ferroelectric going from one end to the other, it overshoots it and in the process creates defect. And these 3 things, you can use the same fundamental principle to solve it. This one was one of the best paper in IDM because this increased the lifetime by 5 orders of magnitude using the same strategy that was used to solve the strategy for MEMS. So this is one thing why one should look at this problem together rather than individually. The second is that because they are together, you can, if you want to make a transistor out of them, then you can also use the similar mathematical formulation. So for example, in here we show that whether you make a transistor based on ferroelectric or based on MEMS, they have fundamental lower limits of the subthreshold swing that you cannot violate. And then you can combine them to make structures that has no classical analog. You can put a MEMS on top of this gate, and you can come up with a structure that has properties that no other devices, classical devices, would have. And thereby, you can come up with a lot of ideas about how to make devices based on these structures. So the final thing I want to show you is about biosensors, and then I will conclude. So this has to do with fractals. So when I started doing this in 2005 or so, everybody, because there's a lot of funding, so everybody was trying to make a biosensor. And anytime you make a biosensor, you publish the result. And therefore, some people would have nanomolar, attomolar, whatever results come out, you publish a paper, because there's no reference. If tomorrow I came back and says that I found a picomolar sensitivity sensor, nobody can, they can check my process, but since there's no limit, no fundamental limit, so therefore nobody can complain about my results. So this is the status of the field. It turns out that there is a very simple way to look at this entire field. And the field is essentially, this is a simple problem of molecules diffusing to a sensor of a particular geometry, and the receptor molecules, the ability of the receptor molecules to catch the target molecule. If it's a virus, you want to catch the virus. If it's some other DNA, you want to catch them. This is very simple problem of three-dimensional diffusion with a surface-specific capture. Because depending on if it's a cylinder or if it's a sphere, then you will have different capture. Now, it turns out you will have to burn many computer hours in order to solve this problem, because three-dimensional complex systems. It turns out that if you know fractals, then you immediately realize that the solution of this equation is really one line. It has the density of the analyte, this red analyte. Ts is how long do you have to wait. Lower the density, you have to wait longer, because the molecule has to swim and then land on the sensor surface. And df is the fractal dimension of the sensor. So if it's a two-dimensional one, you will have 3 minus 2 divided by 2, so which would be square root of Ta. That's the diffusion slowdown. For a cylindrical sensors, df is 1. So there is no diffusion slowdown associated with cylindrical sensors. So essentially, you can just in one line, you can solve this entire problem. And then what it allows you to do is to organize all the sensors in the field. So you can say the sensors in 1970s, why they cannot go below a micromolar. The nanowire sensors, how they can go to the picomolar or so. If you make a nanonet sensors, the nanonet doesn't mean that if you have one wire, multiple wires are better. Not really, because nanowire is sort of in between a planar and a single wire. Its performance is always going to be defined by this. If you thought nanowire is better, and you say that, okay, I'm going to make a nanosphere sensor. If one is better, then sphere would be even better. Turns out, sphere cannot beat nanowire, because the diffusion limit cannot be beat by this. This has the same diffusion limit as this one. So these are automatic things that tells you what you can and cannot do on these structures. And so we wrote a series of papers, and last year, in fact, there was one review paper which collected everything, no matter what mechanism, and was plotted, and it is exactly the relationship that I showed you in the previous curve. It has the same slope, df3 minus df over 2, and essentially you can describe the entire structure that way. So let me conclude. So my conclusion is this. One aspect of electronics is, of course, we can keep pushing this microprocessor-based high-performance structures. The other aspect is that we can learn things from how this one captures things. Like it beats this one uses diffusion. And diffusion is the fundamental law of nature. Nature uses geometry and diffusion because drift is expensive. Here, for too long, we have been sort of negligent about the geometry. FinFET is a geometry argument. remote doping, like that's the geometry, trying to confine things in 2D. So we are gradually waking up, but the nature says that, in fact, this has solved the transport problem in a very fundamental way. In fact, these things, you can show, catches more food by sitting, by not moving, but rather playing with the geometry. And it optimizes between transport and capture in a fundamental way, because this is a natural experiment. And it's much less expensive than your microprocessor. So in terms of resources, energy, in terms of function and reusability, it is much more. And the devices that we are looking into, that I was describing, whether it's battery, whether flexible electronics, whether organic solar cells, are all belong to that group, where you are trying to use diffusion in a very clever way, geometry in a very clever way, to solve some fundamental problem. And so therefore, because most of the things are done in the close to equilibrium thermodynamics, right? An egg is hatched very close to thermodynamics. You don't need 1100-degree furnace to hatch an egg. So this type of thing would probably open up a new direction for electronics. So my final point is that complex need not be complicated, as I showed you this. And it's very similar, that if you don't know how to draw a band diagram, of course, every device looks different, and every device looks complicated. But once you know how to draw a band diagram, life becomes simple. What I'm trying to say is that there is a set of concepts from percolation, fractals, and from this phase transition, very basic concepts. And once those are understood, then a whole set of devices where it becomes very simple to analyze and engineer. So that's all I had. Thank you very much for your time.